of Department of Biomedical Engineering, City University of Hong Kong. He received his bachelor's and master's degree from the University of Cambridge, UK, and the PhD degree from the Harvard University under the supervision of Professor Robert Wood in 2014. His graduate work was centered on the dynamics and control for insect-scale flapping wing robots. Dr. Pakpong's research interest is on the applications of control and dynamic system theories to address challenges in biological-inspired robotic systems, flapping wing robots, macro aerial vehicles, the use of the intelligent mechanism to solve dynamics and control problems, and enhancing the performance of robotic devices through improved understanding of interactions between actuation, dynamics, control, and environmental factors. Okay, now let's give our warmest welcome to Dr. Pakpong.
Yeah, thank you. Thank you for the introduction, and thank you, Professor Sun, for the introduction and for the invitation to this webinar. It's my pleasure to be here, and good afternoon, everyone. So I suppose I can start. Right. Okay. Good. Yeah. Thank you. So as Professor Sun mentioned, right? So today I will be talking about aerial robots and how some aspects such as mechanism and dynamics can be incorporated to basically improve or enhance their performance, right? So it will be rather, I hope this will be rather light, and also in the meantime, interesting and educational. So if you have also in the meantime, if you have any questions, like feel free to interrupt me or take a note, and you can also ask me afterwards. So so thank you again for joining us here. Right. So I'm gonna begin very easily with maybe a video, right? When we talk about aerial robots, I think nowadays many of you will probably have a picture or a vision of this kind of robots in mind, where you can see it's basically a drone or a quadcopter that basically you can find that in the markets, and they're sold everywhere, right? And this is a video of you can see a swarm, a team of drones, right? This video is made by Lexus as an advertisement, so it's also heavily graphic, meaning not all you see is actually real, and you can see a swarm of drones like flying into the sky together, right? So that's why I say it's from Lexus, right? So talking about drones, right? And before we talk about the technical aspect, right? I would like to also go back a little bit before the development of these machines, flying machines. We have to talk first probably about model organism or our inspiration to fly. So what you're seeing here is a footage from BBC documentary, which you can see birds, right? Which are basically our probably motivation or our inspiration to actually take up the challenge to create a flying machine in the first place. And you see these majestic animals. They could seamlessly perform flights and for example dive down into water, right, very impressively, and there could be tons of them. There could be flying fish, right, which gives us a lot of ideas and inspiration to fly. And one thing you might want to take note is how different they are to those drones that you see just now, right? So moving forward to another example that people usually probably kind of ignore or overlook them, right? Insects, or in this case, flies, right? They also very small animals that can perform really agile flight. They can do, you can see they can jump, they can land upside down, and they take off effortlessly, very easily, without too much thinking, right? And they are also relatively primitive animals, meaning they don't have a big brain, they don't have a super power autopilot that we try to develop, but they can also perform these maneuvers very impressively that we cannot almost replicate. Well, it's a true engineering challenge to actually try to achieve something at this level of accuracy or performance, right? Apart from that, I also want you to see how these insects like flies, right? Which is actually also very different from a plane, an airliner, very different from quadcopter or multi-rotor drones. Also, they're also different from birds, where you can see that they're flapping their wings, right, back and forth 100 times per second. Now, so technically speaking, right, what's the differences? Why do they fly differently? Why do they have different mechanism of flight? Right, it comes down to something more fundamental. It comes down to physics. It comes down to the interaction between surface, mechanical surface or wings with the air, which is fluid. So when we talk about fluids, what we have to understand, right, in order to fly, you have to basically generate some force to push the air down, and then use the reaction force that push the body or the machine up to stay in the air, to stay aloft. Now, when we talk about fluids, what matters is Reynolds number. What matters is Reynolds number. Reynolds numbers, if you are a mechanical engineer, you probably have learned about this. It's a ratio, it's a dimensionless ratio between the amount, the size of inertial forces or to the viscous forces. Initial forces means, for example, MA, mass time acceleration. To viscous forces is basically the losses, the energy force that accounts for energy loss in your system, in the fluid, right? This Reynolds number, right, is a ratio of inertial to viscous forces. So the Reynolds number of different flyers are not the same. And as it turns out, larger flying machines, such as planes, have very high Reynolds number. Smaller flying machines or insects have lower Reynolds number. This is because inertial forces scales with the mass, okay, which if you define R to be a characteristic length, it's basically energy times the volume or R cubed. In the meantime, viscous forces is basically coming from losses. These are generally surface losses. They scale with the size of the surface, or R squared. So in the end, this Reynolds number scale as R, roughly speaking, right? So smaller robots, smaller Reynolds number, larger flying machines, larger Reynolds number. Now the problem is here, the viscous forces is where you lose the energy, right? So smaller robots relatively loses more energy in comparison to larger flying machines. So in the end, it means that it's more difficult for small things to fly because you lose a lot of energy in order to be able to stay in the air. And as a consequence of this, you can, for example, look at, right, flight time of a robot plotted as versus as a function of mass. And you'll see, for example, that if you look at a drone, right, in the order of 100 grams, or sorry, my cursor is not really shown. Okay, right. So if you look at a drone in the order of 100 grams or a kilogram, those drones can fly for 20 minutes, 1 hour, right? But when you scale down the drone to something smaller than 100 grams, 50 grams, 30 grams, the flight time becomes really short, becomes 5 minutes, 2 minutes, 3 minutes. And it's the same way where airliners, basically flying machines, are really large, can fly for hours, can fly across the Atlantic, can fly for 10 hours, 20 hours, right? Because they're actually relatively more efficient. They lose less energy from viscous forces. right? So the challenge here in creating something smaller that can fly is the energetic efficiency. And as a consequence of that, the flight time of small robots goes down as the mass goes down. Right? Now, so it means that if you would like to actually make something, right, as big as an insect or as light as an insect to fly, you actually have to do something. You have to do something. It's harder, right? So this is also the reason why in insects you can fly. The flight mode, how it flies, is different from birds, right? They try to actually compensate from the reduction in the energetic or aerodynamic efficiency by using some phenomena, aerodynamic phenomena known as unsteady aerodynamics. The unsteady aerodynamics basically is generated from the flapping wing motion, where the wing keeps moving back and forth in cyclic motion. And by doing so, at this range of low Reynolds number, there are aerodynamic phenomena such they're known as delay stall, for example, rotational circulation and wave capture. But okay, put them aside, right? If I don't want to confuse you with the technical terms. What's happening is that even with the flapping, repetitive cyclic flapping motion, the air surrounding that, the particle of air, right, the motion, the dynamics of the air, of the fluids around it, actually are not cyclic. They don't actually repeat. They become sometimes what people call unsteady, right? And with that, it can somehow, okay, generate more lift than you would typically expect from airplanes or birds, right? And this is kind of a very important finding that explains how actually insects fly. It was first elaborated in detail by Dickinson and Sanjay in this seminal paper in 1999, 20 years ago, that was published in Science, right? So it means that, okay, in early 2010s, right, 10 years ago, right, my then PhD advisor, Rob Wood, initiated this project at Harvard University to try to create a small flying robot, right, using the same principles of flight as insects. And as you see, I was fortunate enough to be a part of the project. And what we did was we developed this small flapping wing robot that has 2 wings on the side that demonstrated, okay, the first flight. It was published in 2013, but the actual flight was actually late 2012. But anyways, this, okay, basically is basically the evidence of how, okay, we can learn from nature, and we learn not just to imitate, right, insects, but we actually learn to understand the underlying flight principles of insects. How can they fly, and why, if we want to make something small as insects to fly, we should try to imitate them, right? We need some basic engineering understanding from that. So I'm not going into the details yet, but over the years, right, this robot, okay, we have been working on for some time, and over the years from 2013 to for example 17, we have made progress. Apart from simple flying, we could also, for example, fly against disturbance or fly outwards against the incoming wind. And in this case, what you see in the video is a slow motion video where the wings are actually flapping in the order of 120 times per second. And it's flying against wind that it's not particularly strong, 80 centimeters per second, but for that size of the robot, that's actually the same as going through the air that is 20 body lengths per second. In comparison, it would mean for an airliner such as 787 to be flying at 1,000 kilometers per second, or even more than that. So meaning this is actually not a trivial task to actually achieve, right? So over the years, okay, we have shown some results, such as, for example, simple trajectory following, or on the bottom right, doing aggressive maneuver where the robot can perch right on a vertical wall using a little bit of help from a magnetic wall, but then the maneuvers is also based on a simple learning approach, right? So these are kind of the example of achievement over the years. But now, what I would like to show you or talk in a little bit more detail is that these robots, they are actually really light, really small, right? The weight of that is 80 milligram. In comparison, if you're an engineer, you work with small stuff, you might be familiar with an M2 screw, meaning a screw with 2 millimeter diameter. An M2 screw weighs around 200 milligrams. So this robot is more or less 2.5 times lighter, or a paper, or it's probably, yeah. Now, the challenge here in making something small is not just making it small, but it's also about actuation and fabrication, manufacturing, meaning you want to create mechanical parts and actuators that are first small. Second, it can withstand forces, because the flapping, they're not stationary parts. They're parts that will be moving, that will be creating force, right? So it's also different from, for example, parts in your mobile phones, where they're mostly static parts that are put together. These are mechanical, like moving parts that basically the wing have to flap 100 times per second, meaning the flying for 10 minutes means you're going through 10,000 cycles of repetitive motion, and it has to survive that, right? So as you can see, the parts of these robots are basically relatively simple, because at the end of the day, they have to be put together by hands and glued together manually, right? So it's created from carbon fiber that are laser cut at high precision. We use fabrication method that is created by stacking multiple layers of material, glue them together, laminate them together, and cut, and then basically fold them together like origami. You can refer to the literature for more details. I'm not going to go into that. But one thing I want you to see is that there are two wings. There are two wings. There are two actuators. Those actuators you see are piezoelectric actuators. One actuator drives one wing. So at the end of the day, you have two actuators. There are nothing else. There's no onboard power, no battery, no computer, no CPU, no microprocessor, no computation, because at 80 milligram, it's still really limited, right? To put everything on board. Even right now, almost 10 years, like from then, we have been making progress on trying to put everything right on board, but we're not there yet. There's some progress, but we're not there yet. We don't have a autonomous system yet. So in this system, you can see that like next to me here is a wire, right? Which is basically plugged in to an amplifier for driving, for creating, for sending the electrical signals that is computed, right, generated from a huge computer off board, right? Because simply, as you know, this robot takes too much energy to put the battery on board, and also too much, we don't have budget enough to put microprocessor or anything on board, right? So it comes down, the reason for that, as I said, comes down from the challenge of, right, so this slide is repeated, the challenge on the energetic cost of flying at small scale. So even though if we somehow make, say, radical, significant improvement, we're still limited by this scaling laws, right, which is a result from physics and Reynolds number. Even if we can do something, we probably cannot expect the flight time of the small flying insects to be very long. Probably realistically, 1 minute would be super impressive, would be extremely impressive already. So there's still a few things we have to do in order to make these robots eventually be useful, right, in actual applications. So in the meantime, we can think of, for example, right, you can be a little bit visionary, you can imagine, right, if you can put some sensors on the robot, then you can use small robots as, for example, mobile sensing network, or use that for sensing gas or doing surveillance or inspection. But in the meantime, if you cannot fly for a really long time because your power consumption, right, is severely limited, right, then you could employ a strategy such as perching, which obviously is a bio-inspired strategy because birds and insects also do not fly all the time. You can do strategy, you can employ strategy such as perching for energy saving, so that you can continue to your mission to act as, for example, a mobile sensor node. Why not flying? Right? So what we did, for example, in this case, was to develop an electrostatic actuation, sorry, not actuation, electrostatic adhesive pad. We mount that pad, it's a very light pad, 13 milligram. We mount the pad on the robot and control the high voltage on the pad and show that this robot, with this idea, this robot can, for example, perch or stick to a ceiling that is made of multiple materials, glass, wood, and natural leaf, right? And we can seamlessly take off. And because of the nature of this electrostatic adhesion, the power consumption of this is extremely small. So in the order of 1,000 times less than flying. It means that if you can fly for 1 minute, you can probably stay perched for an hour or a few hours, right? So this is kind of some ideas that, of course, is still work in progress, that it will have to be materialized and is still waiting for the robot to be untethered, but it doesn't prevent us from solving the problem from multiple aspects at the same time, right? Now, I'm gonna come back to a little bit more educational slide again, right? The reason I was talking about perching is this, and the demonstration of perching is an idea that we did try out is this, right? So earlier slide, I showed you something very similar equation, very similar analysis, right? Showing you that Reynolds number for smaller robots is smaller, meaning it's less efficient to fly. Now, for perching though, when you consider whether your robot will be able to perch or not, very fundamentally, what you consider is whether the adhesion force you can generate, in this case from an electrostatic adhesive pad, can overcome the weight of the robot. Now, whatever kind of adhesion you use, right, adhesion is actually generated, is going to be surface forces. It's going to be one of surface forces. You can amplify that by having a larger surface, but at the end of the day, the size of your surface will be limited by the size of your robot. So if you consider the ratio between surface force over the weight of the robot that you have to overcome, right? That ratio depends on the length scale R as R squared, surface force over the weight R cubed. So at the end of the day, it becomes 1 over R, meaning for smaller robots, surface force becomes larger in comparison. So it becomes a dominant factor. It dominates the weight. And this is why, we could actually perch with smaller robots, such as a robotic insect. Now, in order to try to just use the same principle and apply to a larger flying machines, such as planes, airliners, it would be almost impossible, or it's going to be extremely difficult, because fundamentally physics is not in your favor if you want to try that on a larger robot, right? And this is why it was a good demonstration for an insect scale robot. Now, what about something in between? Because even when we talk about quadcopters or multirotor robots, right? They come at different sizes. For robots that people use for industrial application, for example, DJI Matrix 100, this is kind of a well-established platform, weighs 2.5 grams. But in the meantime, smaller platforms, such as this Crazy Fly, weighs about 30 grams. And if you look at their flight time, right, 30 minutes is fine, it's good for application. 5 minutes is about like borderline useless. So in the meantime, like smaller quadrotors, not just insect scale robots, still suffer from their low energetic efficiency. But perhaps, right, they can also employ a similar strategy, such as perching, to help them overcome some difficulties, to make them more useful. And of course, people have done that, right? So these are, for example, some examples from different groups. The one from Illinois on the left, and on the right one is another robot. So what you could see here are basically relatively small quadrotors. They're not in the size of a kilogram. They're probably in the size of a few hundred grams that can actually perch, okay, on a window or on a ceiling, used by incorporating, right, several actuators and mechanisms into it, right? So these are good examples, but in this case, we were thinking, can we do better, right? Can we do better? Because for these robots, they still have to carry extra components, such as gripper, servo motor, in order to be able to perch and take off from a surface. And extra masses is not good, it's not great. So we propose to, for example, in this case, use the aerodynamic interaction between the spinning propeller and the ceiling for the robot to actually perch on the wall, or sorry, to actually perch on the ceiling. And in this case, we demonstrate that when the robot is very close to the ceiling, okay, it can generate the same amount of lift force, but with significantly lower power consumption. Meaning, even without any mechanism, without doing anything to the robot, just having some simple structures for preventing the robot from directly crashing into a ceiling, you can actually stay at high elevation at the ceiling and in the meantime, reduce the power consumption by, for example, 50%. So you can actually stay aloft for much longer. And in another demonstration that probably don't want to talk too much is, for example, we create a simple mechanism. Again, this robot doesn't have extra actuators. We just have very simple mechanism that allows the robot to actually perch on a wall. And when it's perching on the wall, you can see the propellers are not spinning. The propellers are not spinning. Most propellers are not spinning. Only one propeller is spinning at very low speed. So it means that it's actually using very little energy, right? It can take off and again, perch on the ceiling. And again, by using relatively little energy. So for example, this traditional robot, the robot itself can fly for 5 minutes. When it's perching on the wall, it can stay there for almost half an hour. And we don't actually need to have extra actuators. So the whole package of the robot remains close to 30 kilograms, the original weight of the robot, right? So we don't actually compromise the flight time by putting more parts onto the robot in order to be able to perch, right? Now, I'm gonna come back. So my talk is a little bit going around. a little bit, and also it seems to be unstructured, but it's actually one story that keeps going. So I want to come back, right? So I went from small flying robots that are insect-like to small quadcopters, and they share the similarity in terms of difficulty in terms of power and energy. Now, if you come back to look at them a little bit on another aspect, you see stark differences between two platforms, right? But one thing I want to bring up right now is the fact that for the quadcopter on the left, it has 4 rotors, 4 propellers, right? And this is more or less the established platform design that, of course, you can have more rotors. In a bigger platform, sometimes you see 6 rotors, but you rarely see anything, I say the word rarely, right? But you rarely see anything with less than 4 rotors. But on the other hand, on my previous flapping wing robot, I have 2 actuators and 2 wings. So how do they work? Okay, how do they work? So for flight, a very simple explanation for a flying robot, the requirements for them to fly is that first, they have to be able to generate thrust force to stay up in the air. So the thrust is acting against the gravity. And in the meantime, you have to make sure that it remains more or less, to be able to hover, it remains more or less upright. This means it can control its orientation. It can control its orientation. As a mechanical engineer, that means the ability to generate torque about 3 body axes. And in aerospace engineers, the terms are row, pitch, and yaw torque. Basically, it refers to rotation about 3 perpendicular orthogonal axes, row, pitch, and yaw torque. Now, with robots, okay, with quadcopters, you have 4 actuators, right? So in the simplified model, what you can think of is you have 4 actuators. You can have 4 driving signals. You can control 4 quantities. And basically, you can create a map between these 4 driving signals to 4 motors, to 4 outputs, thrust force, and row, pitch, and yaw torque. So 4 inputs, 4 outputs. That's straightforward. That's how a quadcopter can fly. And that's why you see a quadcopter with 4 rotors in general, right? Now, for flapping wing robots, this is very different. You have 2 actuators. How it works is they are piezoelectric bimorph actuators. When you drive, when you feed in the driving signal, you can create the bending motion at the tip of the actuator for the actuator to bend left or right. This motion at the tip of the actuator is coupled to the motion of the wing through the transmission to create a flapping forward and backwards motion. So if you apply sinusoidal driving signal for the actuator to create kind of sinusoidal output at the tip, then this is translated to sinusoidal flapping motion of the wing. But sinusoidal flapping motion of the wing, look at my hand here, alone would actually not generate output force for the robot to fly. How the robot fly is actually, the robot can fly because at the wing, there is this passive hinge, meaning it's just a hinge that is not actuated, that allows the wing to rotate along the other axis, right? This is called wing pitch rotation. And this rotation is passive. So when the robot is actuated, the wing sweeps forward. The air forces the wing to rotate along the passive hinge and back and forth. And this actually passive rotation here, the wing pitch rotation, which is passive, which is caused by the air, right? By the air, is actually allows the wing to pitch. And then in the meantime, when the wing has this pitching motion, instead of non-pitch motion. This wing pitch motion is actually the mechanism for generating the lift force in the upwards direction, as you can see in the video. So it means that, okay, by sending different sinusoidal driving signals to the wings, we can generate thrust, roll pitch. We can regulate thrust, roll pitch, and yaw torque. For example, you have two wings. If you flap one wing larger, right, one sinusoidal signal is larger than the other sinusoidal signal, you can create a roll motion because the wing that is flapping at larger amplitude will be generating more lift, and you create a roll torque. You can also shift your stroke, right, to the front of the body or to the back of the body to generate pitch torque. And also, if you actually don't employ symmetric forward and backwards flapping motion, you flap forward faster, flap backwards slower, you can also create a yaw motion or yaw torque. So this is how you can actually use two actuators with sinusoidal signals, driving signals, to generate four outputs, right? For the flapping wing robot to fly. So thinking, right, back and forth between these two platforms, you can also ask yourself, right, so if you have only two actuators on a multi-copter robot, on a drone, on a multi-copter drone, on a conventional drone, can you actually fly with only two actuators? And the answer is actually yes, you can fly. And I'm going to show you first how this flies. Right. It flies like this. It flies by spinning. Right. But basically, the force generated by the propeller is pointing up. So that's how it flies. So again, right, for a normal quadrotor, you have four propellers, four actuators. You can change the force, the signals between these four to generate four outputs: roll, pitch, yaw, and thrust. Now, if you have only two propellers, what you could do is you can control two things. So first thing you control is the thrust by controlling both propellers together. Spinning faster, you get more thrust. Spinning slower, you get less thrust. And in the meantime, in this figure here, if you spin one propeller faster than the other, it will generate more force. It will generate roll torque. Right? But don't forget that in the video I show you, the robot is actually spinning. So if it's spinning, right, about the yaw direction, it means that at some moment later, okay, what you think as a roll torque will become pitch torque. Meaning for one moment, you can control pitch torque. For one moment, you can control roll torque. And by combining them together, you can think of it as you can actually control pitch and roll torque together as a vector of torque in the horizontal axis. So to realize this, okay, don't worry if you don't understand, but my short explanation is that you want to control pitch and roll torque together, and you ignore your torque. You let the robot spin, you don't control that. So you only control three things: thrust, pitch, and roll torque. Pitch and roll torque is about the timing when you apply the torque, right? Because it depends on your orientation. So pitch and roll torque can be controlled together, and thrust can be controlled separately. So in order to do that, in order to do three things, control three things, we don't use we use two driving signals, but we introduce sinusoidal driving signal to the robot, right? So if you have two driving signals on the left-hand side, T1 and T2, both of them are sinusoidal driving signal. You can control the thrust by shifting T1 and T2 up and down. You can control the magnitude of the torque as the amplitude of the driving signal. the amplitude of the torque, and you can control the direction of the torque, whether it should be pitch or roll or in between, by changing the timing of the driving signal. So at the end of the day, you can see that this driving signal, sinusoidal driving signal, is similar to the way how robotic insect is controlled. So we can control that. That's why you could fly in the previous, as you see in the previous video. But now I also have a question. So now we show that I can have a robot with only 2 propellers and it can fly. Can we do something more fun? And yes, we can. For example, we can make a robot that is basically starting as a quadcopter or quadrotor, right? And then it can be split into 2 bicopters. So it can be split into 2 robots because you only need 2 to fly, 2 rotors to fly. So we made this robot, for example, that's starting off as a quadcopter, and then it can be split into 2 bicopters. And this video is showing, for example, a robot flying as a quadcopter. My student, Song Bai, came in, right, split it into 2 robots, and both also can fly. And we can even do better than this, as we made a second generation of the robot. This is larger. So we have a robot taking off in a quadcopter mode. And then during mid-flight, this robot splits into 2 robots that they can fly and be controlled independently. So if 2 robots has to, for example, follow 2 targets, you can do that, right, with this. So, okay, so far, this is not a conclusion. I will speed up a little bit. But so far, okay, this is to make my talk a little bit more structured. I've shown you, right? We use kind of Perching mechanism. We use mechanical design and mechanical solutions, such as Perching mechanism, right? Simple Perching mechanism to solve the problem of power, right? We use passive mechanisms such as wing hinges, right? In flapping wing robots to allow 2 actuators for the robot, flapping wing robot to fly, right? To have 4 outputs, roll, pitch, and yaw torque. We use the same principle of dynamic inputs for driving the actuators, even on motors, in order to create a bicopter that can fly, right? So we use this kind of mechanical solutions intelligently to solve problems in actuation, under actuation and control and power problem. So are there actually other things we can do, right? Other problems we can solve? What about more popular problems such as in flying robots, such as sensing, navigation, and computation? Can we use mechanical parts to do computation or to solve computation or sensing problem? And the answer is sure, we can try. Okay, so this is more of a recent work that we have done more recently. This is a robot, a quadcopter, but it doesn't look like a conventional quadcopter. It has tilted propeller and with some mechanical structure, we call it ducts, right? They are ducted propellers attached to that. So what we did was we made this robot. We put it next to a wall, to a surface, and we measure the force generated by the propeller, right? So in a normal situation, right, the thrust generated by the propeller will be more or less perpendicular to the propeller axis, right? Now, so it will be in that direction. Now, when it's near a wall, what we find, and we can explain this to some extent, is that this force will change because of the interaction between the air and the surface. This force, if you look at the 2 components, in the vertical component will become smaller. In the horizontal component, it will become larger. What it means is when this robot, right, is near the wall, the horizontal component of the force will be amplified. And that amplified force will push the robot away from the wall. Right, will push the robot away from the wall, will prevent the robot from colliding into the wall. And in the meantime, when you actually, as it turns out, when you actually a little bit further away from the wall, the reduction in the vertical force will change the torque of the robot, will make the robot turn towards the wall. So at the end of the day, as it turns out, okay, if you have a robot and a wall, this robot will fly towards the wall, but it won't actually crash into the wall. There will be an equilibrium point somewhere, right? A small distance between the wall and the robot. And this robot, as you can see, has no vision, no sensing. So it doesn't know where it is, but it will align itself next to the wall, and it won't collide with that. So this is an example of how you can create a design, right, for the robot to interact with an environment. And in the meantime, it's the mechanical design, it's the mechanism, it's the aerodynamics interaction. It's basically doing the sensing job and controlling job at the same time, right? So it virtually senses where the wall is, and it controls itself to be next to the wall. So as a result of this, it means that you can also use the robot outside, and you can fly along the wall without any camera, without any sensors for sensing where the wall is, for example. So there are also other things that we could do. For example, you can create some computation into a robot airframe such that when it makes a collision, it reconfigures itself so that in this case, it's a protective airframe for the robot. So that when it crashes, when the robot has a collision, it falls up to basically create a cage that encloses the middle of the robot where it houses electronics, so that that part remains undamaged and safe. So there are ways that you can actually use mechanism without actually sensor, you see, without no computation, without actuator to achieve functions, So this is kind of basically the idea of using mechanical intelligence to solve some physical problems, to replace some calculation and sensing, right? And that basically is the theme of the talk. So I believe, right, in the end, from these examples, you can also think of other tools and solution, other tools based on this kind of set of thinking, right? Mechanical and dynamical intelligence to solve problems in other domains too, and maybe not limited to aerial robots. That's something that probably is a take-home message for you. So, so here are probably some. I'm concluding, so I'm wrapping this up. Here is probably some other works that may not really fit into the theme, but may be interesting for you to look up if you would like to see. So there's an example of soft DA, basically dielectric elastomer actuators that are used to create small flying robots. There's a example of visionless strategy for two robots to cooperate together, or also the idea of modular flying robots that you can see. So if you're more interested, you can of course look at our website. So lastly, I would like to thank my collaborators, my colleagues, and my students, and who actually have contributed to whatever you have seen, right, so far, and also for other things that we have produced too, and of course the major funding grant, RTC of Hong Kong, right? So yeah, that will be more or less the main talk. So thank you, and yeah.
Thank you so much, Pakpong. Now let's move on to the Q&A section. So is there any questions from the audience?
Any questions? Welcome. Or if you like to type your questions in the chat box, you can also type on it. Or you are also welcome to speak. Just unmute yourself and you can ask questions on the spot. Okay, any questions? No, no questions. It's very clear.
Maybe
David has questions,
yes,
I believe.
This question will encourage others to ask more questions. So it's a simple question. So yeah, Pakpong, thank you very much for giving this very impromptu talk to our department. Thanks a lot.
Thank you.
Very much appreciated. Maybe if you can share some thoughts about what is the, I mean, you shared pretty well the theme of your talk, and you ended addressing that initial question. But maybe could you maybe share a bit more on what is the next thing that you want to do? What are the new questions, the new ideas that you and in your group are currently trying to explore?
Okay, sure. Thank you. So, well, what I could disclose, for example, there's some ongoing works, right? So we are still, so you see that, relatively speaking, people might think that aerial robotics are relatively mature right now. You can see commercial products. You can see people using them for agricultural, for filming, right? But those are one of a very mature area is sorry, not mature, but well-researched area is estimation, sensing, navigation, right? Now, basically it comes down to autonomous navigation, which is a very hot topic as it's also tied to AI, intelligence, computer vision for creating, constructing, recognizing here what is in front of me, how to, get from point A to point B, right? And it's the same, it shares some challenges with, for example, self-driving cars. Now, those problems can be solved to some extent. The problem, the challenge here is they can be done with, say, neural chips, AI, computer vision, lots of sensors, right? For self-driving cars, you need computation and sensors. So the problem comes back to how do you make that possible with smaller robots that may be 100 grams? Because for urban applications, smaller robots, lighter robots are safer. So a lot of challenges comes in, or regulations come in when you want to operate this robot. For example, in the UK or in the States, if your robot is more than 250 grams, you need a license, you need a permission to operate. So those 250 grams becomes a number where, below this, what can your robot do? Can you make something that is useful, but not just a toy that is lighter? So can we do more, right, with lighter robots? So can we actually do more by getting rid of parts, by not adding more parts, by not adding actuators, by not adding heavy payload, but achieve the same thing? Can we do more than that, right? That's actually kind of one of the motivation or where our research directions are going to.
Okay, thanks. Just a really quick follow-up. So are you trying to do that navigation through, this last idea that you presented of doing mechanical and dynamical computation, somehow less way to do computing and some decision making? Are you if you can disclose it, trying to follow that very secretive actually, to follow that direction.
Sure. For example, the last example I showed is basically a simple way to stay next to a wall. So we can, for example, expand from there. Can we actually go to an entire building using that mechanism? And in the meantime, maybe, for example, for search and rescue operation, you can still stream out the video back to the user or record the video for later use, but you don't have to do heavy computation in real time. So if that can be done, it could still help with search and rescue operation, for example. Yeah. Mm-hmm. Thank you.
So any other participants you would like to ask questions? Welcome.
This is a bit like my classroom recently.
How do you force them to ask questions then?
You have to ask them first.
We go to the list and like,
Right.
mini more. You ask a question.
You might not get
students here. Just name your student. Ask questions.
You might, you might not have attendance if you don't ask question.
Yeah, yes. That should be one of the requirements, Karen. If you really wanted the attendance certificate, ask a question.
Wow.
Right. Type down a question.
Okay, no questions? No questions, that will be the end of this webinar then.
Okay, that's sure. That's okay.
Okay, Dr. Sun, David, any other questions?
Okay, if you do not have any questions, okay, let me end this seminar. So thank you all for attending. See you next month.
Happy New Year to everyone. Happy New Year.
Happy New Year. Thank you so much
Happy
for
New
the
Year.
invitation.
Okay then, thank you. Thank you. Thanks again, Dr. Pakpong, for the seminar, and thank you all for participating this webinar. And we will have another webinar in the coming month. You're welcome to join again. So that's the end of today. Thank you very much. See you then.
Bye. Thank you. Happy New Year.
Thank you. Thank you, Dr. Pakpong. See
Let's
you.
hope 2022 is a good year. really, I really wish everyone in the world that, you know, we need this. So, yes, we need a good year, really.
Yeah.
Finally.
Come back to normal.
Sure. I hope so too.
We
Okay.
can have physical seminar in the coming year. Okay, then anyway, bye-bye.
Bye-bye.
Thanks.
Bye-bye. Thank you.
Bye-bye all.
Thank you.
Thank you. Bye.
Bye.